So we are still going through chapter 23 and electric potential. And today I'll try to solve these problems. So the quick reminder, electric potential was defined as the electric potential energy per unit charge. And we could write it in terms of electric field as a line integral like this. Basically, potential between B and A, VB minus VA, which we show with VBA, which is a scalar number, is equal to minus the line integral from A to B, E dot dl. And for example, we calculated the electric potential of a charge sphere. We found something like this. It was falling with 1 over r outside, but constant inside. And pay attention, if you take the derivative of this potential, it's going to be 0 inside, which is the electric field. And derivative of 1 over r is 1 over r squared outside. So we talk about the electric potential of point charge. We also introduce a way to calculate electric potential of continuum of charges via integrals. For example, electric potential of a ring was of this form. Electric potential of a disk was of this form. And by later, I think we introduced something called equipotential surfaces or equipotential lines or equipotential volumes, which was the space in which 2 points had no electric potential difference. Let me clean this up from last week. Okay. For example, equipotential lines of a parallel plate was like this, these green lines. Equipotential lines of a charge, point charge was like concentric shells. Equipotential lines of dipole was like this, and so on. We calculated the electric potential of a single dipole, and we found something like this. And we compared it with the electric field of a dipole, which was going with 1 over r cube. And finally, we said we could determine the electric field from electric potential by simply taking the derivatives. So if you calculated V, each component of electric field can be calculated by taking the derivative along that component. And we showed it with our examples for ring and disk. And I think we later introduced electrostatic potential energy, and we defined something called electron volt, which was, as its name says, was an electron and volt. It was like an electron charge times volt, and volt was joules per coulomb. So electron volt was actually a conversion from joules to a different unit, which was more suitable for small charges. And this is the conversion factor. And I think we solved this problem, right? So now suggested problems, let's start with this guy. So a non-conducting sphere of radius R0 carries a total charge Q distributed uniformly throughout its volume. Determine the electric potential as a function of distance R from the center of the sphere. For R greater than R0, for R less than R0, and we take, as usual, V is equal to 0 at R is equal to infinity. And C plot V versus R and E versus R. Maybe I can write the definition of electric potential. V BA was equal to VB minus VA, and it was equal to what? Exactly, right? Line integral of electric field minus integral from A to B dl, which is a vector, dotted onto electric field, which is another vector. Right? So we need electric field. And now we are pro electric field calculators because we know the Gauss's law, right? And I think it doesn't require any calculation outside, exactly like you said, outside E is equal to 1/4 pi epsilon naught. Total charge is Q divided by R squared. Any objections? So inside, I need to do a little bit of algebra. Inside, let's do it here. So it was like E dot dA and E times 4 pi R squared is the area. On the right-hand side, I have total charge inside, which is rho, which is 4/3 pi R cube. Okay, maybe I can do it like this. Total charge divided by 4/3 pi, total charge divided by total volume R0 cube times volume, which is 4/3 pi R cube. Divide this whole thing with epsilon naught. So 4/3 pi, and I have R squared, R cubed, and inside, let's write it here, is equal to, okay, maybe E is equal to 1/4 pi epsilon naught Q, what is it? Q times R/R0 cube. Now, potential, these were electric fields. Potential, let's start with A, outside. VB minus VA is equal to minus E dot dl from A to B, which is equal to, okay, let's put 1 minus 1/4 pi epsilon naught. So I have this guy, Q R squared. If I take the integral of R squared, it is minus 1/R, and that minus will cancel with that minus. So I can just write 1/R plus, and this is going to be from, let's say, some R, and let's take B to infinity. Okay. And if we take V of R is equal to infinity, you can solve this equation for VA. Okay, if we put this 0, then V of R will be just that guy, right? 1/4 pi epsilon naught. Okay, there's overall Q over R. Could you repeat the last part that you wrote R and it became positive? Which part? Or the integral? So let me do it carefully. I was trying to rush it because, okay, it's like 1/4 pi epsilon naught Q over R squared. And now dl is dr. It's radiated out every time. And this is from A to B. And this is equal to, okay, there's like a minus here, and there's 1/R squared. And I know integral can be done by asking what is what should I take the derivative of that should give me this expression. And that one is what? Minus 1/R. If you take the derivative, it's like 1/R squared, right? Then the integral of this thing is minus 1/R. And there is one more minus here, one more minus here. So the overall thing will be positive. So it's going to be 1 1 over 4 pi epsilon naught q over r, and the integral limits. And integral limits go from r to infinity, and this is equal to what? If you put infinity, it's 0 minus 1 over 4 pi epsilon naught q over r. But I remind myself, what is this? This is equal to VB minus VA, which is r, and VA, this guy is 0 because it's at infinity, so VA is just this guy. Now let's do it inside B. So we can do it like from like somewhere inside up until the surface. Let's do this. Like let's do the surface B. Maybe I can do it. V surface. Maybe let's do the general form, and then we can put what B is. VB minus VA is equal to minus some R inside to R0 on the surface. And the electric field is 1 over 4 pi epsilon naught q over r0 cube times r dr, and this is equal to minus 1 over 4 pi epsilon naught q over r0 cube times 1 over 2 r squared from r to r0, and this will be equal to minus 1 over 4 pi epsilon naught q over r0 cube 1 over 2 r0 squared minus r squared. And now we can put what we found for surface, which is we can just put surface to this guy and solve it for VR. Then VA will be, V of R will be V surface, okay, V of R0 plus, okay, this guy plus this guy, and I took this guy to other side. So this is gonna be one, okay, actually let's write the surface too. The surface we know it's like 1 over 4 pi epsilon naught q over r0 plus 1 over 4 pi epsilon naught q over, so r0, I have r0 cube, r0 squared, this is q over, oops, q over r0 times 1/2 minus 1 over 4 pi epsilon naught q over r0 1/2 r squared, something like that. And you can combine these two. Actually, I can do that here, right? So I can put this 3 and I can delete this guy, just combine these two. And now I have a little simpler expression. Oops. Good. Any objections? And now let's plot this. Okay, let me try to plot this. Maybe I can first start with electric field, because actually I can do them both here. Maybe let's do this here. So let's do first. One and second one. So let this be E, let this be V, let this guy here be R naught. And for electric field, inside it's kind of like increasing linearly. And when it hits the surface, it decreases with 1 over R squared. And for electric potential, I can first write outside because it's simple. It's like 1 over something like 1. Maybe I can do a little bit over something like this. This is 1 over r. This is squared. This is 1 over r. And inside, it is decreasing from like a larger value, right? This is some larger value to this, and they should match at the surface. So I'll write it like something like that. It's like some quadratic decrease, something like that. All right, next question. A flat ring of inner radius R1 and outer radius R2 in the figure carries a uniform surface charge density sigma. Determine the electric potential at points along the axis. So we can probably use our result from ring. Does anybody remember the ring? Or maybe it was, let's check it. I think it's somewhere over here. Okay, here I just copy. Of course, if you can't remember, you know how to derive it too. It's exactly the same, right? So this is, maybe I can put it here and delete this guy so that we have space. Now this is, I will choose a ring on a disk. So let's choose a ring like this. And we will call this dV. And there's like a charge on it, dq. So this dV is equal to 1 over 4 pi epsilon naught dq divided by x squared plus r squared. And dq, I know how to get this. dq is equal to 2 pi r dr, this is the area, times sigma, or I think they give us the sigma. I can put this and integrate both sides to get what? Like V is equal to 1 over 4 pi epsilon naught. Let's take the integral from R1 to R2, 2 pi r dr, let's write sigma outside, divided by x squared plus r squared, something like that. And the trick was u squared is equal to x squared plus r squared, and u du was equal to r dr. And if you do this, v is equal to, okay, think, copy, paste, and integral limits. And it should be, okay, maybe there's also 2 pi here. And u du divided by square root of u is equal to u. And this will go from u is equal to, okay, x squared plus r1 to x squared plus r2. Something like that. U cancels as usual. Okay. Maybe pi's cancel, and the result is sigma over 2 epsilon, and open the parentheses, square root x squared plus r1 r2 squared minus x squared plus r1 squared. All right, and I think that's it. Next question. Okay. The charge on the rod in this figure has a uniform linear charge distribution. Lambda is equal to A times X. And we want to determine the potential V for all points along y-axis, and B for points along X outside the rod. So we want to determine potential somewhere here and somewhere here, right? So I choose like a chunk and write its potential. Let's first fix our reference point, right? The problem doesn't say it, but I can tell this is x is equal to 0. That's x is equal to L, and that's x is equal to minus L. And the charge density, lambda, is equal to some A times x. So it's like negative here, positive here, right? Because x is negative here, right? Now, I want to write this element here. Let me draw it something like that. So that's x, that's some, call it, that's y, and this, we know how to do the Pythagorean theorem. It's like x squared plus y squared. Oops. Right, put this in. V is equal to integral over all little elements d, now it's x, and I think it's going from minus L to L. And charge is A times x with the appropriate units for A, and this should be divided by the distance, which is x squared plus y squared. And I forgot to put 1 over 4 pi. One over 4 pi epsilon naught. All right? Any objections? Good point. It's even. Actually, the integral is odd, right? There's like x to the power 1. So everything else is even. So do I have to calculate this integral? What's the result of integral? Good. Yes, thank you. That's 0. I don't have to deal with this, because I look at it and I can see it's going to be 0. And actually, I could see that it was 0 from the beginning, because this is like a negative charge. This is positive charge. We know for every negative charge, there's a positive charge, and potentials will add up to 0. But it doesn't hurt to like write the integral and then see it one more time. Right? Now B, let's choose our point now here. Maybe I can do here. And now I want to call, okay, this guy is, I need to choose a different variable. Let me call this R. Then this is R plus X, or actually that X is actually negative side. So it's, I don't like that negative side X. Let me put it like this. Now it's like a positive X. So this is X. So this, oops, why am I doing that? I don't need that guy anymore. I think you remember that. So this is X, this is dx. All right, and its distance is R minus X. Good. Let me write this now. V is equal to, let's put 1 over 4 pi epsilon naught, integral over all x, and x goes from, again, I think, minus L to L, and this time charge is A times x divided by divide this by with the total distance, which is, I think, r minus x. Yes, good. Now, what do I do with this integral? Of course, you know what to do. You can just go to Wolfram alpha and write it, and whatever the result gives, you can just copy it. That's fine by me. But I can calculate this integral. It's not that hard. So I can do it like minus r plus r, and the thing inside is going to be, okay, let's do this. This thing is going to be the x, so there's like a minus 1 plus r over r minus x, something like that. And now I can integrate one by one. The first one is going to be minus x from minus L to L. And the second one is going to be r log, maybe I will call ln r minus x. Even, is there a minus? Yes, there's also a number of minus. That also has the same limits. Maybe I can push this a little bit. That's also minus L to L. And that integral is equal to minus L minus L, right? That's basically, okay, maybe I can do it like this, not to mess up. Minus L minus L, okay, that makes more sense. Minus R, I'll write this as log R minus L divided by R plus L. And this thing is equal to minus 2L minus R log R minus L divided by R plus L, something like that. Any objections? Then V finally is 1 over 4 pi epsilon naught. And this is like minus 2. Okay, there's also A here. Minus 2L minus R minus L over R plus L. Okay. One more. Okay, let me clean this. A lot of things to read, but I think let's see what it is. A Geiger counter is used to detect charged particles emitted by radioactive nuclei. It consists of a thin, positively charged central wire of radius RA. Okay, this one has radius RA, surrounded by a concentric conducting cylinder of radius RB. This one has radius RB with equal negative charge. Good. The charge per unit length on inner wire is lambda in units of coulomb per meter, and the interior space between the wire and the cylinder is filled with low pressure inert gas. Charged particles ionize some of these gas atoms. The resulting free electrons are ejected towards the positive central wire. If the radioelectric field is strong enough, the freed electrons gain enough energy to ionize other atoms, causing an avalanche of electrons to strike central wire, okay? Generating an electric signal. Okay, blah, 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 blah. Find expression for electric field between the wire and the cylinder and show that the potential difference between RA and RB is given by this. Okay, I think you more or less got the idea. The only thing you've been using more or less here is like VB minus VA is equal to minus electric field from A to B dl dot E. That's what you've been using, and that's the theme of that chapter, seems. Okay. How do I find the electric field? All I want is the VA, VB between these 2 points. So electric field integral will be along this line. So I only need electric field here. How do I find this? Gauss's law, yes. And we know Gauss's law. We can just, I don't know, choose like a cylinder to enclose some amount of charge. We know it's going to be radially outward, and the area times electric field is equal to charge inside divided by epsilon naught. Let me just write it like this. Okay, maybe I can do this. Gauss's law, I think E dot dA is Q enclosed divided by epsilon naught. E is E times A is 2 pi R times, I don't know, let's call it H is equal to Q enclosed is like saying that, okay, the wire unit in has like a lambda, charge per unit length. That's good. That means it's like lambda times, what did we use? H divided by epsilon naught. And E, I think we already knew this formula, right? These guys cancel. 1 over 2 pi epsilon naught lambda over R. Any objections? Let's push this a little bit. And he is here. Okay. Now let's use the first formula. VA, B, okay. They are asking about A and B. So I can just write it like VB minus VA is equal to minus DL is DR from some RA to some RB. Or actually they use uppercase R. It's called RA to RB. This is uppercase. This is uppercase. This is uppercase, which doesn't matter, but fine. 1 over 2 pi epsilon naught lambda over R. And this is equal to minus 1 over 2 pi epsilon naught lambda. Okay, maybe I write the integral and ask you dr 1 over R R A RB. So what is this? Yes, thank you. This will be equal to minus 1 over 2 pi epsilon naught lambda ln RB divided by RA. Also, I am assuming everybody knows this, right? Some some ln x minus ln y is equal to ln x divided by y, right? Everybody knows this, so I didn't mind to show this. But if you don't, that's it. That you don't need to know anything else. And now it is asking, okay, we found VB minus VA, but it's asking VA minus VB. So we just know how to take the minus sign. The result is VA minus VB is equal to lambda divided by 2 pi epsilon naught ln RB divided by RA. And that's the